What you've done so far has been what's called the traditional hypothesis testing method. By comparing your test statistic from your sample to your critical value, you're able to make a conclusion. Another method you can use is called the p-value method, which this one is actually the one that gets used more frequently, I would say. So what a p-value is, to start with, it's the probability that we get a test statistic from our sample that is at least as extreme as the one representing our sample data by random chance, assuming that our null hypothesis is true. So it's basically like, hey, assuming my null hypothesis is true, what's the odds that I get a sample where the data is this extreme? If those odds are really low, then you probably are going to need to conclude that your null hypothesis is not correct. So to determine this p-value that's going to allow you to make your conclusion, it is based on your test statistic and your normal distribution. So if you have the alternative hypothesis being a less than, your p-value is the area to the left of your test statistic. If you're looking at an alternative hypothesis with a greater than, then the p-value is the area to the right side of your test statistic. And if you're looking at a two-tailed test where your alternative hypothesis is not equal to, this one's a little bit weird because your test statistic is just one single value from your sample, but your p-value is actually twice the area to the right or left side of that test statistic. So say maybe my test statistic's down here. My p-value is actually take that area and multiply it times 2, because we're going to reject in the case that our sample data is either too small or too large. So we're going to practice finding some p-values. So here we've got a significance level, an alternative hypothesis, and a test statistic. So we're going to start with our test statistic, which is z equals 1.18. And then since our alternative hypothesis is instead p is greater than 0.25, we're going to have the area to the right of that test statistic be our p-value. So if I look at my normal distribution and I find the probability that z is greater than 1.18, I'm going to look at 1.18 on my table and then subtract that probability from 1. I'm going to get a p-value of 0.1190. You might have noticed that I didn't use my significance level, but that's because the significance level is compared to your p-value to determine the result of your hypothesis test. You don't need it to find the p-value. Okay, so let's do another one. Again, we're going to start with our test statistic of z equals negative 2.16, and then looking at our alternative hypothesis, which is less than. That's going to put my p-value to be the area to the left of that test statistic. So using my normal distribution, I can find the probability that z is less than negative 2.16, which I can just look at on my table and get 0.0154. Then we've got one where your test statistic is 2.34, and your alternative hypothesis is that p is not equal to 0.25. So my p-value, is going to be twice the probability that z is greater than 2.34, because we're rejecting our null hypothesis if either p is larger or smaller than 0.25, so I have to double it. So if I do my probability, I'm just going to look at negative 2.34 on my z-score chart and then multiply it times 2. I'm going to get 0.0192. So in order to make an initial conclusion using a p-value, what you want to think about is your significance level, which when you're thinking p-value method, I would think of it as the cutoff that you've set for deciding that your result from your sample data is too unusual to have happened when your null hypothesis is true. So you're going to reject your null hypothesis if your p-value that you get from your sample data is less than the significance level that you've chosen. So say, for example, that you have a significance level of alpha equals 0.05 and the p-value you got from your sample data is 0.10. then you would fail to reject your null hypothesis because your sample data that you got could have happened by chance 10% of the time and still had your null hypothesis be true. And we set a cutoff saying, hey, this sample data needs to be unusual enough that it would only occur 5% of the time or less in order to reject. We're going to go back to our previous examples and determine what conclusions we should make. So now we're actually using our significance level and comparing it to our p-value. So our significance level is 0.05 and our p-value is larger than that. So we're going to fail to reject our null hypothesis. Now, when you kind of word it, there's multiple ways that you could explain. I'm going to say that our sample data that we have could have resulted by random chance in 11.9% of the cases where our null hypothesis is true. So that means that our sample is not super unlikely to occur given that our null hypothesis is true, and it's more likely than our cutoff of 5%. So if we look at another one here, we've got our significance level of 0.01, and my p-value is again larger than that, so I'm going to fail to reject my null hypothesis. Although if you look at our p-value, it seems pretty small. It's only 1.54%, which is fairly unlikely to occur if we're assuming that our null hypothesis is true. But it is still larger than the cutoff that we have set for alpha of 1%. So we will fail to reject. Okay, last one here. Significance level is 0.05 and my p-value is smaller than that, which means we will reject our null hypothesis. If we assume the null hypothesis is true, this sample should only happen 1.92% of the time, which is pretty darn unlikely, and it's less than the 5% cutoff that we have set, so we will reject. Okay, we're going to do one all the way through and kind of compare our two methods. So we've got a CEO of an electric utility company claiming that more than 70% of his customers are satisfied with their electric service. Before we start, we need to verify that we can actually do this hypothesis test. So using either method, we need n times p to be greater than or equal to 5 and n times q to be greater than or equal to 5. So our values for p and q are going to be 0.7 and 0.3. And if I multiply those by my sample size of 100, it's definitely going to be greater than 5 in both cases. Also a random sample, it says, and it is binomial because they either are or are not satisfied with their electric service and all the other requirements to be binomial. Okay, so to state our null and alternative hypothesis, first let's write out our claim symbolically. Its p is greater than 0.7, and then our other situation is p is less than or equal to 0.7. And I'm going to flash back up here for a second because I realize it's kind of conflicting. The last line says more than and the first line says at least then, so I'm just going to edit and say that we're doing strictly more than instead of at least. And then back to our alternate hypothesis is going to be p is greater than 0.7, and our null is, as always, p is equal to, and then 0.7. So all of this beginning stuff is the same no matter which method you are using. We're going to need our test statistic in both cases. So if we plug in our values, p hat from our sample is 80% of the customers say they are satisfied. So 0.8 minus 0.7 over the square root of 0.7 times 0.3 over 100 is going to give us a test statistic of 2.18 for our sample. Now here's where things diverge a little bit. So let's start with our p-value. So using my test statistic of 2.18 and my alternative hypothesis being greater than, my p-value is going to be the probability that z is greater than 2.18, which if you use your normal distribution table is going to be 1 minus 0.9855. It should be, although I didn't write it, 0.0145. because I was trying to subtract in my head and yeah, got the wrong thing there, but 0.0145. So based on that, If you look at my p-value and compare it to my significance level, which is 5%, my p-value, the odds that the sample happens when my null hypothesis is true, is only 1.5%, which is less than my significance level cutoff of 5%, so we are going to reject our null. If I was going to do this traditional method with my critical value, I'd use my significance level and my alternate hypothesis to get my critical region. So now I'd be looking in my z-score chart for the z-score that cuts off 5% to the right, which is 1.645. And then using my critical region, if I look at my test statistic of 2.18, it is in that critical region, so I will reject. Same conclusion I got with my traditional method. So if I'm gonna word my final conclusion in terms of my original claim, then let's look here. I'm rejecting my null hypothesis. My claim corresponds to my alternative, so since I am rejecting my null, that means I'll be supporting my alternative hypothesis and supporting my claim. So I'm going to say there is enough evidence to support the CEO's claim that at least 70% of his customers are satisfied with their electrical service.